Hello J2s, welcome to the second lecture of carboxylic acids and derivatives. Now, let's do a quick recap of what was covered in the previous lecture. Alright, we talked about how to name carboxylic acids, the physical properties, some of the physical properties of carboxylic acid. We also touched on acidity, okay, important concept of why acids, alright, are stronger acids than phenols and alcohols, and how do we compare the acidity of different carboxylic acid. I hope you can still remember some of these concepts that we have discussed. Next, we move on to preparation of carboxylic acids. So mainly via oxidation and by hydrolysis. And lastly, we began discussing about the reactions of carboxylic acids.
As mentioned during the last lecture, there are three categories of the type of reactions that carboxylic acids can undergo. So in the last lecture, we already talked about the reactions involving the cleavage of the OH bond in carboxylic acid. And these reactions are mainly due to the fact that the carboxylic acids are acidic. So we talk about acid-metal reaction as carboxylic acids reacting with metal to give you salt and hydrogen. We also talk about acid-bases reactions. Alright, so under acid-base reaction, the carboxylic acid can react with a base like NaOH, or it can also react with a carbonate like sodium carbonate, or hydrogen carbonate like sodium hydrogen carbonate. So for the reactions with carbonate and hydrogen carbonate, the reaction will have evolution of CO2 gas, and these reactions can also be distinguishing tests for carboxylic acids. Next, we will move on to reactions involving the cleavage of the C single bond O in carboxylic acid. We have got condensation reactions resulting in the formation of ester. We also will talk about how to form acyl chloride. And the last type of reaction will be reduction, and we'll discuss more later on. For now, let's look at how carboxylic acids can undergo condensation reactions.
So the first reaction we're going to talk about today is condensation, right? Formation of esters. Now, please take note that this is not a new concept, as we've covered it in hydroxyl compounds. We have learned that carboxylic acid and alcohol can react together to give an ester. All right, of course, we need a few drops of corn H2SO4 and as heating under reflux. This type of reaction is known as condensation. So if you are asked to give the type of reaction or to suggest the type of reaction, please make sure you write it as condensation. All right, if you recall earlier, we also talked about what is condensation reaction. It's when two molecules join together with the loss of a small molecule in the process. So you can see that in this process, all right, water is actually the small molecule that is being eliminated. Now, this is a slow and reversible reaction. Okay, you can see the double arrow, and usually it will only come to equilibrium or reach an equilibrium after a very long period of heating under reflux. Okay, and I would also like to highlight corn H2SO4 has two roles in this reaction. Okay, it first acts as a catalyst to protonate the carboxylic acid. Now, if you take a look at the mechanism on page 13 of the lecture notes, you will see that actually that's what's happening in the first step. However, you're not required to know the mechanism, all right? And the second role of corn H2SO4 is dehydrating agent, all right? Because it will help to react with water that's formed from the reaction. It will then shift the position of equilibrium to the right, and in the process give you a higher yield of the ester. Okay, so how do we know that the carboxylic acid and alcohol react in a certain manner? Which are the bonds that are being broken in this condensation reaction. We use this method known as isotopic labeling, where we use an alcohol that contains the oxygen 18 isotope. So once we have done this isotopic labeling, you realize that the results show us that the reaction occurs with the CO bond cleavage in the carboxylic acid and the OH bond cleavage in the alcohol. All right, because in the water that is produced, it doesn't contain any oxygen 18 isotope. Okay, for this water here, it doesn't contain oxygen 18 isotope. So the oxygen 18 isotope actually appears in the ester. Okay, and the H2O eliminated, you can see that it's actually from the breaking of the C single bond O in the carboxylic acid, as well as the OH bond in the alcohol. Okay, also take note that carboxylic acids do not react with phenols to form esters. Okay, the reason being phenols are actually weaker nucleophiles than alcohols. Okay, why is that so? Now in phenol, the lone pair of electrons on oxygen is delocalized into the benzene ring. Therefore, what we will have to do is we will have to convert phenol to phenoxide, which is a better nucleophile, and then react it with acyl chloride. Okay, we'll talk more about this reaction later on when we come to acyl chloride. Okay, now once again, all right, type of reaction is condensation reaction. Okay, the mechanism is what is an addition elimination mechanism. You can take a look at the lecture notes for more details on page 14. However, all right, it's not required in the syllabus. All right, and in this mechanism, the alcohol is acting as the nucleophile. Okay, two carboxylic acid molecules can also come together, right, in a condensation reaction to give you an acid anhydride. Okay, so this ethanedioic anhydride that you see here is a type of acid anhydride. All right, and the mechanism is also addition elimination, as what is previously covered under the formation of ester. Okay, but in this case, of course, then the carboxylic acid is the nucleophile.
Next, we'll take a look at the formation of acyl chloride under the reactions involving the cleavage of CO bond.
This is a type of nucleophilic substitution reaction. You will see that the OH in the COOH group actually will be substituted, all right, to give you Cl. The OH will be substituted to give you Cl in this in the acyl chloride. Okay, there are three main ways of converting carboxylic acid to acyl chloride. So you can react the carboxylic acid with PCl5, PCl3, all right, or SOCl2. This is rather similar to the reaction between alcohol and PCl5, PCl3, and SOCl2 to give you a alkyl chloride. Okay, and the condition for all these reactions are at room temperature. Okay,
the last reaction of carboxylic acid that we are going to look at will be reduction. And the reduction, we will be using the reducing agent LiAlH4, lithium aluminum hydride.
Okay, in hydroxyl compound, we have learned about how to prepare alcohols, and one of the ways described is to reduce carboxylic acid and from there you will get a primary alcohol as the product. All right, we'll use the reducing agent LiAlH4 in dry ether. All right, but the reduction of carboxylic acids, please note, is more difficult compared to that of aldehydes and ketones. Right, as carboxylic acids, they are less easily attacked by nucleophile. We have talked about this in the last lecture. As a result, reducing agents such as NaBH4 and H2/Ni cannot be used. All right, they are not strong enough as reducing agents to react with a carboxylic acid. So in these two reduction examples given here, let's try to write out what are the products after the reduction of the carboxylic acids shown on this slide. Okay, so if you have CH3, CO, CH2, COH, all right, the carbonyl group as well as the carboxylic acid group will both undergo reduction with LiAlH4 in dry ether. All right, so the ketone will actually be reduced to a secondary alcohol, and the carboxylic acid will be reduced to a primary alcohol. Okay, so we will balance by adding plus 6H, all right, to show the reduction process. Okay, and on top of the one more product that we form is water. Now, let's take a look at what if we have used another reducing agent, NaBH4. Now, it's the same compound as the first equation. Take note that because NaBH4 is a milder reducing agent as compared to LiAlH4, so it will be more selective, and only the carbonyl group, all right, the ketone here, will undergo reduction with NaBH4. Once again, I would like to highlight that carboxylic acid, the COH group, cannot be reduced by NaBH4, as carboxylic acids can only undergo reduction with LiAlH4. So the product, okay, it will be CH3, CHOH, CH2, COOH. And to balance the equation, we will add in 2H, okay, H in the square brackets. All right, I hope you've copied down the text in blue. On to page 15.
Okay, so after going through the different reactions carboxylic acids can undergo, let me now present the summary chart to you once again. We have three types of reactions of carboxylic acids. The first type of reactions involve the cleavage of the OH bond. This is where you learn carboxylic acid can react with metal, bases like your NaOH, as well as your carbonates and hydrogen carbonates. The next type of reaction would involve the cleavage of the C single bond O. Okay, so under these reactions, we learned about condensation reactions that carboxylic acids can undergo. And carboxylic acids can form esters with alcohols, and this is what we call condensation reactions as well. Carboxylic acids can also react with PCl3, PCl5, SOCl2 to give you acyl chloride. This is what we call nucleophilic substitution reactions. Lastly, carboxylic acids can undergo reduction using LiAlH4. They will then give you primary alcohols when they get reduced using LiAlH4. So I hope you have now remembered the reactions of carboxylic acids that we have just discussed.
We'll now move on to some special reactions, all right, that will happen to methanoic acid and ethanedioic acid. Now, these are very exceptional cases, all right, so you have to remember them by heart as well. Okay, so first of all, methanoic acid, HCOH, as well as ethanedioic acid, COH2, they will be oxidized by acidified KMNO4. And these, all right, methanoic acid will be oxidized to CO2 and H2O. All right, I've included the structural formula for HCOH here. And ethanedioic acid will also be oxidized to 2CO2 plus H2O. Okay, now take note that all other carboxylic acids will not be oxidized by KMNO4, acidified KMNO4. Therefore, all right, these are special reactions that you will need to know, all right, and know by heart as well. Okay, and the other special reaction, right, that involve methanoic acid is the oxidation of bivalents and Tollens reagent. Now we talk about valence and Tollens reagent in the previous chapter, carbonyl compound. Now if we were to draw out the structural formula of methanoic acid HCOH, we will see that there is a aldehyde-like, CHO-like portion. As a result, okay, when we react the methanoic acid with valence reagent, we'll see a brick red PPT. And if we react the methanoic acid with Tollens reagent, we will see a silver mirror. All right, so these results actually can give a false positive result when testing for aldehyde. All right, again, I must stress, methanoic acid is not an aldehyde, but because, all right, in the structure, right, there's this C double bond OH group, okay, therefore it is kind of like a special case, all right, whereby you have a carboxylic acid that can give you a brick red PPT with valence reagent and silver mirror of Tollens reagent. So take note of this. Okay, we'll now move on to the next part of the lecture, which will be on carboxylic acid derivatives. In particular, we will be looking closely at acyl chlorides as well as esters. Okay, so what are actually carboxylic acid derivatives? So they're actually compounds that you can get from carboxylic acid. All right, so the structure of carboxylic acid derivatives, you will see the acyl group, which is the RC double bond O group. All right, so I have a few examples of carboxylic acid derivatives over here. First one is an acyl chloride. Acyl chloride, all right, you would be able to identify this C double bond OCl group. Next, ester. Okay, this is not new to you. All right, the C double bond OO, all right, the ester bond is something we've talked about before. Then we will also have amide, C double bond O NH2. Not to worry, we'll cover amides in greater detail in our next chapter on organic nitrogen compounds. And we also have an acid anhydride over here, where you have C double bond O and bond is bonded to another C double bond O. All right, acid anhydrides are not in the syllabus. Okay, so for carboxylic acid derivatives, all right, these will be the main few points that we're going to cover. Firstly, let's take a look at the nomenclature. Okay, for acyl chlorides, we will replace the oic acid with OR chloride. So what does this mean? Okay, so if you take a look at this CH3 C double bond OCl, all right, if it had been a carboxylic acid, then we will have named it ethanoic acid. But in this case, it's an acyl chloride, so it'll be ethanoic chloride. The next example, all right, if this had been a carboxylic acid with a COOH group directly bonded to the benzene ring, we will have named it benzoic acid. But in this case, it's a COCl group, all right, bonded to the benzene ring. Therefore, we will replace the oic acid and it becomes benzoyl chloride. Okay, next, how to name esters, all right? There are two parts to the naming of the ester. All right, the first part comes from the alcohol portion, and the second part comes from the carboxylic acid portion. All right, for the alcohol portion, we'll change the alcohol to alkyl. All right, so if it's from ethanol, we'll change it to ethyl. And for carboxylic acid portion, the carboxylic acid will change from oic acid to OAte. Let's take a look at some examples. All right, if we have CH3COOCH2CH3, right, you would be able to identify that the red portion here comes from the alcohol ethanol. All right, so the alcohol portion, we put it as an alkyl, it will be ethyl. Then the black portion over here, you can see that it's from the carboxylic acid, ethanoic acid. Ethanoic acid, now they will react together to give you the ester ethyl ethanoate. All right, so the ethanoic acid, you change it to ethanoate, that will be the second part. So what I want to highlight here is when you see the structure of an ester, you need to first identify which part comes from the alcohol, which parts come from the carboxylic acid. Now, let's take a look at the next example. All right, for this example here, again, I've highlighted the alcohol portion in red. It may be easier if you rearrange, all right, the groups a little bit. You will see that the red part is from the alcohol to methyl propanol. Okay, so you can convert it to an alkyl group, you'll be 2-methyl propyl. And the black part over here is the carboxylic acid portion. It's from ethanoic acid. So the second part of the name of the ester will be ethanoate. Okay, so this is how you go about naming the ester. And the last example on ester, all right, the red part is from phenol, so phenol, and the black part is from the carboxylic acid, so it's phenol benzoate. Okay, but take note that a phenol and a carboxylic acid will not react to give you the ester. How can we form this ester? Then, all right, we will have to use acyl chloride instead of carboxylic acid to react with the phenol, and we must also add in NaOH. We'll talk more about this reaction later on. Okay, let's move on to amide. For amide, we change the oic acid to amide. So if we have CH3COH is ethanoic acid, so CH3CONH2 will be ethanamide. All right, and in this case, all right, 3-bromobenzoic acid, we change it to 3-bromobenzamide. Okay, and acid anhydride, we change acid to anhydride. Okay, so I think this is fairly straightforward as well. Okay, next, moving on to the physical properties of carboxylic acid derivatives. Okay, now, if we have acyl chloride and ester, and we would like to discuss the boiling point, okay, but before that, we have to look at the intermolecular forces of attraction. So these acyl chloride and esters, they are actually polar. So there will be PD-PD interactions between the polar molecules. Right? If you want to compare the boiling points to that of carboxylic acids and alcohols of similar MR, the boiling points will be lower. All right, because carboxylic acids and alcohols are capable of intermolecular hydrogen bonding. Whereas for acyl chloride and ester, they can only have PD-PD interactions between the molecules. All right, there is no hydrogen bonds between the molecules of acyl chloride and ester because there's no protonic H. In other words, there's no H bonded to OF or N, hence not able to form intermolecular hydrogen bonding for acyl chloride and ester. Now, if we look at amide, however, all right, amides are capable of intermolecular hydrogen bonding. So we can have hydrogen bonds between the amide molecules, all right, as there is a H bonded to N, all right. In fact, there are two H's bonded to N. So comparing the boiling points of amides to other carboxylic acid derivatives, I'm not talking about carboxylic acids here, but other carboxylic acid derivatives such as ester, acyl chloride, their boiling points will be higher, especially if they have similar MR. Because recall in the previous slide, all right, the other carboxylic acid derivatives that they are like esters, acyl chloride, they are only capable of PD-PD interactions between molecules. All right, but for amide, they are capable of forming hydrogen bonds between the amide molecules. The next physical property we'll talk about is solubility in water. Okay, now take note that for this R group, all right, the hydrocarbon group, they are not able to form favorable interaction with water molecules. So as the size of the nonpolar hydrocarbon group increases, the compound becomes less soluble in water. Okay. Now, for acyl chloride, okay, they can hydrolyze rapidly in water, as you can see in this equation. All right, if you put in an acyl chloride in water, you'll get a carboxylic acid for NHCl. So in other words, they react with water, yeah. And of course, this will also mean that they are soluble in water. For ester, they are slightly soluble. Okay, yes, no doubt they're able to form hydrogen bonds with water molecules. Okay, this you can see there's a lone pair on oxygen that can form the hydrogen bonds with the protonic H of the water molecules. Okay, but we also have the non-polar hydrocarbon chain, right? The R and the R prime over here. These groups, they do not have any favorable interactions with water molecules. Okay, as a result, esters are only slightly soluble in water. And then, how about for amide? Fairly soluble. All right, as you can see, amides are capable of forming hydrogen bonds with water molecule, and they have also more sites for the formation of hydrogen bonds as compared to esters earlier. Okay, so fairly soluble. And then now let's take a look at the reactivity of the different carboxylic acid derivatives. So for these carboxylic acid derivatives that you can see here, acyl chloride, amide, ester, and acid anhydride, they do not undergo typical reactions of carbonyl compound, although you can see the C double bond O group. All right. In fact, most reactions convert one derivative into another and into the carboxylic acid. Okay, so let's take a look at what are some of these reactions. So most reactions proceed via the addition elimination at the carbonyl carbon. All right, so you can see that the group Z, right, is replaced by a nucleophile. You can also call this the nucleophilic acyl substitution. All right, nucleophilic acyl substitution is not the same as the SN1, SN2 nucleophilic substitution. Okay. Then now, next, we'll move on to talk about acyl chlorides first in greater detail, and then followed by ester. Now, acyl chlorides are highly reactive. We'll take a look at hydrolysis and how acyl chlorides can form esters and amides. So as mentioned earlier, acyl chloride hydrolysis in water. So this reaction we call it hydrolysis or nucleophilic substitution. So what happens is that the OH, all right, will replace or the Cl, okay, and water over here is actually acting as the nucleophile. All right, and it's a very vigorous reaction at room temperature. All right, the Cl minus is actually a good leaving group, and you can see that the resultant solution is acidic, all right, due to the formation of HCl. Okay, so this is hydrolysis of acyl chloride. It will react vigorously with water at room temperature to give you the carboxylic acid as well as HCl. Okay, another thing to note that is because of the formation of HCl, all right, and you know that in water, right, HCl will dissociate to give you H plus and Cl minus ions. We can, if we add in AgNO3 to the resultant solution, we will actually form the AgCl PPT, so we can observe a white PPT being formed when we add in AgNO3 to the resultant solution. So this also becomes a distinguishing test for acyl chloride. Okay, we'll now take a look at the hydrolysis of benzoyl chloride. For benzoyl chloride, all right, it's much less reactive than your alkyl acyl chloride. So it actually only reacts with water rather slowly. All right, and if you recall in the previous slide, we talked about alkyl acyl chloride reacting vigorously with water. So why is it that for benzoyl chloride, all right, it's much less reactive? Now, the reason is due to the delocalization of electron density between the p orbital of Cl, carbonyl pi bond, and the pi electron club of the benzene ring. So as you can see, I've drawn out all the p orbitals and they overlap. So the lone pair on Cl, all right, in benzoyl chloride, in other words, the lone pair can delocalize into the pi bond of the carbonyl and also into the benzene ring. All right. As a result, the carbon in the C double bond OCl group is less delta positive, is less electron deficient. Okay, so the reaction, the reactivity towards nucleophile will also be less. Okay, we'll now take a look at the relative ease of hydrolysis comparing that of acyl chloride, alkyl chloride, and aryl chloride. Okay, so for acyl chloride, if you add in water at room temperature, all right, it will react with water vigorously. For alkyl chloride, you will have to add in NaOH as well as heat. And for aryl chloride, all right, there is no reaction, all right, even if you add in NaOH and heat. So why is that so? Okay, now for acyl chloride, you will notice that the carbon, the electron deficient carbon, is bonded to two electronegative atoms, all right, oxygen and chlorine. So it is highly electron deficient. Okay, the delta plus is very big. So it is easily attacked by nucleophiles. All right, so you don't need any heating at room temperature and water. It will undergo hydrolysis. That's for alkyl chloride. Okay, it is only the carbon with the delta positive, the electron deficient carbon is bonded to one electronegative atom Cl only. So comparing it to acyl chloride, the carbon delta positive is smaller, as you can see. And in other words, it is less electron deficient than the carbon in acyl chloride. And as for aryl chloride, okay, there is a partial double bond character of the CCl bond over here. Please recall this from your halogen derivative topic. Yeah, partial double bond character as the lone pair of electrons on Cl can delocalize into benzene ring. So this CCl bond is strong, and therefore aryl chloride will not undergo hydrolysis or nucleophilic substitution. Okay, so in the examples given, all right, let's take a look at what will happen. So acyl chloride plus water at room temperature, right, you will get the carboxylic acid and HCl. And if it's acyl chloride and plus 2NaOH, okay, it will also undergo hydrolysis. However, you'll get a carboxylate salt and NaCl and H2O. And for alkyl halide, you will get the alcohol when you heat it with NaOH. And for chlorobenzene, in this case, it's an aryl halide, no hydrolysis or no nucleophilic substitution, even if you add in NaOH and heat. Okay, so these are the difference in the ease of hydrolysis of acyl chloride, alkyl chloride, and aryl chloride. Okay, and as for the formation of ester, acyl chloride can also form ester when it reacts with alcohol. Okay, and in the process, all right, it will eliminate HCl. The alcohol is acting as the nucleophile in this condensation reaction. All right, so this is also similar to the formation of ester by reacting carboxylic acid with alcohol. All right, but because acyl chlorides are more reactive, right, we can more easily react it with alcohol to get the ester. So room temperature will do. Whereas for carboxylic acids and alcohol, we will have to add in a few drops of corn H2SO4 as well as heat under reflux. So the conditions are not quite the same. All right. Okay, but take note that, okay, phenols, they are not able to react with carboxylic acid to give you the ester. All right, the reason is because phenol is a weak nucleophile. All right, so as earlier mentioned, okay, phenol, we will have to convert it using NaOH to a phenoxide anion, which is a stronger nucleophile, and then we react with acyl chloride. Okay, acyl chloride, they are more reactive than carboxylic acid. Then we will be able to get the ester. Okay, so acyl chloride plus phenol, and you add in NaOH, you will then get the ester. Okay, so let's fill up the blanks on page 21. Right, in the example given, the first step is to have NaOH react with the phenol to give you the phenoxide ion first, which is a stronger nucleophile. All right, and then of course to balance the equation, you will also have to balance it with Na plus and H2O. And in the second step, the phenoxide anion will then react with the acyl chloride. Take note, it's acyl chloride here to give you the ester. And to balance the equation, you also have to have Cl minus in the product. Okay, so this is actually how we'll form ester using phenol, react with acyl chloride, and also we have to add in NaOH. Yeah. Okay. Acyl chloride can also form amide. Okay, so this equation will illustrate how this is also a condensation reaction because HCl will be eliminated in this process. Okay, and take note that this is a similar reaction to that between alkyl halide and amine. All right, so acyl chloride plus NH3 in this case can give you an amide, and of course plus HCl. Of course, if we have acyl chloride reacting with a primary amide, we will get, a primary amine, then we can get a secondary amide in this case. And if we react the acyl chloride with a secondary amine, you will get a tertiary amide. Okay, but not to worry, we'll talk more about amides and amines in the next chapter. So we've come to the last part of carboxylic acid derivatives, all right, and we're going to talk about esters. Now, esters can undergo hydrolysis, all right, to give you the products of carboxylic acid and alcohol. However, this reaction is very slow if you heat it with water alone. So usually we add in acid and alkaline, or alkaline and heat, all right, to make it faster. So let's take a look at acidic hydrolysis. All right, for acidic hydrolysis, all right, we will heat with HCl aqueous or H2SO4 aqueous. Okay, this is a reversible reaction. As the products form the carboxylic acid and alcohol, all right, they can react together again to give you back the ester. Okay, recall what are the reagent conditions needed for the formation of ester from carboxylic acid and alcohol. And the second hydrolysis is alkaline hydrolysis. Okay, so for alkaline hydrolysis, we heat with NaOH aqueous. Take note that this is actually an irreversible reaction. All right, so when you write the equation, please make sure that you use a single arrow instead. So OH minus here is actually a stronger nucleophile in this hydrolysis, and the product that will form for alkaline hydrolysis is actually the carboxylate anion. And since it's resonance stabilized, all right, there is little tendency also to react with the alcohol. So this reaction is also known as saponification because traditional salts actually made from the alkaline hydrolysis of esters. On page 24, you will be able to read more about the uses of carboxylic acid derivatives, but these are some of the common uses, right? They're used in essence, perfume, and flavoring material, or used as solvent, or used as medicine. Okay, so in summary, this is what we've covered for the chapter on carboxylic acids and derivatives. Okay,